let's quickly then see. Okay, so this was last year's Sakai final exam question. And it says manganese dioxide catalyzes the decomposition of hydrogen peroxide. First, in that is a very loaded sentence. Okay. First, we need to know, what does it mean if we say that manganese dioxide catalyzes?
Manganese dioxide
is a catalyst. Is it going to take part in the reaction? Yes, as a catalyst, but that's it. It's not going to form part of my reaction equation. Okay, if it is, it's there on the line. Okay, so it's the catalyst, and then it decomposes hydrogen peroxide. What does decompose mean? So it breaks down. So decompose means it is a substance that consists of more than one element, and it breaks it up into its parts. It decomposes. So hydrogen peroxide is H2O2. Hydrogen peroxide is H2O2. So decomposition would break it up into what? Come on. It consists of what? H2 and O2. Okay? So you have to, if you don't know these basic words, and those are really basic things, to understand what decomposition is. What is hydrogen peroxide? Some of them. For hydrogen peroxide, yeah. There's a few. Okay. So usually hydrogen oxide, okay, hydrogen oxide, it's actually dihydrogen oxide, is that. Now as soon as we have one more oxygen, then we put a per in front. So we know hydrogen oxide would be H2O, so hydrogen peroxide would be H2O2. So, for example, manganate is MnO3. Manganate. Can't remember. I think it's 2+ or 3+. Can't remember exactly. But permanganate would be MnO4. Okay. Carbonate. Percarbonate is CO3. Sulfate SO4. Persulfate is SO5. Okay. So when you see that per, just take away the per and see what would hydrogen oxide have been. Oh, H2O. Okay. So per would be H2O2. Okay. Cool. So hydrogen peroxide is manganese dioxide catalyzes the decomposition of hydrogen peroxide solution to oxygen and water. Okay, so in other words, I've even got it wrong. The hydrogen peroxide solution to oxygen and water, not oxygen and hydrogen. Oxygen and water. Okay, so let's just balance this equation. We've got two. We see on this side we've got 3 oxygens. So we'll first mix. Two compounds with oxygen. So we'll first mix with the ones that are there more than once. So for example, if I'm going to add a 2 here, I will see that I've got now 2 oxygens and 2 oxygens. That's 4 oxygens and 4 hydrogens. So I must add a 2 here. and then I've balanced the equation. So I'll first try and solve the ones where there's more than one of that substance in there. Okay, so there's my reaction equation. Okay, they tell us that manganese dioxide, that's the catalyst, was added to a 2 mole per cubic decimeter solution of hydrogen peroxide in a certain flask. So I already have the concentration of the hydrogen peroxide. The flask was connected to a gas syringe, as shown in the sketch. The flask was quickly stomped, and the readings of the volume of the gas in the syringe were recorded. So in other words, if we look at this, what is the product? What are the products that are formed? Liquid, water, and oxygen gas. So in other words, hydrogen peroxide, in here there's the manganese dioxide, it acts as a catalyst in here, and what do you think are we going to see happening here? What is it going to look like? If my reactants, my reactant is a liquid, a concentration. So this one actually looks like this. Okay, that if it's an aqueous solution, it's a liquid. So I've got a liquid on this side, and my products are liquid, is liquid and gas. So what do you think are you going to observe when this reaction is occurring? While this reaction is occurring? You must say something. Think of your reactants. How will you see your reactants forming? What reactants do we have? A liquid and a gas. How are you going to see a liquid form in a liquid? Are you going to see it? No, you won't see a liquid form in a liquid. Okay. What you will see, however, is the gas. How will you see the gas?
You just see it like evaporate.
You won't.
Slowly evaporate, but like inside the flask.
Inside the flask, you'll start seeing bubbles forming. It will start fizzing. That is the gas being released. So here, and where will the gas be released? Well, it will look like it's the manganese dioxide that's fizzing. It's not really. It's because remember, the manganese dioxide just creates that quick route of quickly reacting with the manganese dioxide and then reacting to form the gas and the water. So slowly but slowly, I don't know. I don't think hydrogen peroxide is. I think it's a clear liquid, so you won't see the water forming. If it wasn't, let's say it was. Water had a dark color. Let's just for a moment assume water had a dark color. Then you would have seen around the manganese dioxide the darker color liquid forming and slowly diluting into the rest, and you will see the bubbles going up. Okay, so that's what's happening in here. So bubbles are going up because gas is a reactant, and the bubbles, and because gas is now being released in here, the gas is starting to push on the syringe. And so the syringe is slowly showing more and more gas is being released in this. And so this is what they say. The flask was quickly stomped, and every 1 minute they looked at how much volume has been displaced by the gas. So here, after 0 minutes, there's no volume displaced. 1 minute, there's 10 cubic centimeters displaced. And so every 1 minute, they take a reading. Does that make sense? Okay. First, they ask us to write a balanced equation for the decomposition of hydrogen peroxide. We've done that. Okay? Very important. And look, 3 marks for that. So that is valuable. Now, you have to use graph paper and answer sheet and plot the graph of the volume of gas produced against the time for the catalyzed reaction. So, what we're going to have to do is simply draw, well, they've given you this diagram on the diagram sheet. So this is time and this is volume. So you can either, depending on what you can either measure moles. Moles is difficult to measure because you actually can only measure grams. You can't measure mole, you calculate mole. You measure grams and you calculate mole based on the grams. So the same thing with a gas. We can't measure the grams of gas, but we can measure the volume of gas. Okay, so what we will do is first go to our graph. Let's divide it into 1 minute intervals. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm not going to do all of them. Oh, there's only 10. So let's do one more. Okay, and then this one goes up to 36. So let's do it in 4. So there's 5. Okay, so in 1 minute there's 10. So after 1 minute I'm at 10. 2 minutes I'm at 18. So there's 15. 18 is roughly there. 3 minutes I'm at 24. So there's 5, 10, 20. Wait, 5, 10, 15, 24. Just less than that. Okay. Then 28. 2 less than there. Then 31. 31. Do you notice the shape? I'm not going to do all of them because I think you guys know where I'm going at this. Okay, and so eventually after you've done that, I suggest even with a pencil, you just connect them with a smooth curve, and it should probably look something like that if we plotted all of them. Okay, then they ask us 5 marks. That's lovely. Okay, sketch a graph on the same set of axes than the question we just drew, but for an uncatalyzed reaction. So if we didn't have the catalyst there,
So would it take longer?
it would take longer. So what would that do to my reaction rate?
Decrease
It would decrease my reaction rate. What did I say on a if I have so this is either volume or grams when I plot it from an observation. What did I say? How will I know? Where will I look for the reaction rate? What on this graph represents the reaction rate?
Time taken.
Just a little bit louder. You saw whisper at me. What?
Activated complex.
Where's the activated complex there? Now I said that gradient. The gradient represents the reaction rate. So I must draw a graph. It will reach the same height as this graph, but it will take longer to get to that height, isn't it? And it must have must it be steeper or less steep?
More steeper.
Sorry?
More steeper.
So if I make it more steep, I'm still starting here, and now I'm going steeper and I reach the same height. You see? Am I reaching it sooner or later?
Later.
I'm reaching it sooner. I'm reaching my finished reaction quicker. So definitely not. Remember, the gradient represents the reaction rate. The steeper the gradient, the quicker the reaction is happening. So we must make it a less steep reaction rate, something like that. Okay, it might even go much further than this, but that's all they're going to want to mark on here. I don't know how many marks. Yeah. So I think if they give 3 marks, I don't know, but I think the 3 marks would go 1 for starting at 0 still, 1 for having a gradient less than the gradient you already drew, and 1 for eventually also finishing at the same height. You are still producing the same amount, but you're taking much longer to actually get there. Okay. How long did it take to produce 29 cubic centimeters of this gas? So what you would do is you're asking how long before it takes, this is 5, 10, 15, 20, 13. So how long did it take to get about at 29? Now your graph is going to be much prettier than mine because you're doing it on a graph set of graph papers. But if you go horizontal until you meet it, this is how long it will take, roughly. Okay, you're estimating how long it will take. You could use the table, but you'd see 29 is somewhere between here. So it's somewhere between 4 and 5 minutes. You can't say 4.5, because it's not necessarily 4.5 minutes, because it's not necessarily that halfway. I think it is probable. But even during 4 and 5 minutes, it's not a straight line. And so you can't even take half. It's still a curved line. So it's much better to just use your graph to make that estimation. Make sense? Question 5.51. What trend do you notice from the table as regards to the volume of the gas as time proceeds? What do you notice about the volume of the gas as time goes on?
As time is increased, the volume of the gas is also increasing as well.
Yes, but that's not the complete picture.
Okay, I think after 8 minutes or 9 minutes, the volume of the gas will be constant.
Okay. I would say a little bit more than that, because look at the next question. So whenever you have a 5.5.1, go and read all of the questions so that the next question might not give you a little bit more of a hint onto what they're actually asking. So if you understand, use collision theory to explain your answer. So understand, what are you going to explain by saying the volume is increasing? How does collision theory help you to explain that it is increasing?
I think you're going to use, you're talking about concentration.
Very good. Yeah. So, no. So, if I look at that collision theory, in what they want me to answer at that point, is what am I going to say about collision theory? Where I would use this is I want to talk about successful collisions. But then, how does that have to do? What does that have to do with the production, the volume that I'm supposed to recognize? And for me, and I don't know how to explain this, but for me, I realize that what they want me to say is that as time goes by, there are less successful collisions.
Yes.
Do you understand why are there less successful collisions? Because reaction rate is not about how much is produced. It's how much is being produced per second or per time unit. So what is happening to my reaction rate over time? It's decreasing. My reaction rate is the highest in the beginning when there are a lot of successful collisions every second. But as time goes by, I've got less reactants. Do you understand? There's less of my reactants to have successful collisions. So what is it that I need to notice in volume? I need to see that my change in volume every second is less, every minute is less. In the first minute, I change with 10. Then I change only with 8. Then I change with 6. Then I change with 4. Then I change with 3. then 2, then 1, then 1 again, then I don't change at all. Do you see? So what were you supposed... So in other words, so when it comes to collision theory, they want you to talk about successful collisions. And what is it that you had to recognize about the successful collisions? Every minute there are less successful collisions. Do you understand that? So even though the volume of the gas is 28 in 4 minutes, doesn't mean there's 28 successful collisions. So let's just look at it as, for example, let's say that from 0 to 10 meant there were 10 successful collisions. That's not what it means. But you can almost look at it like that. There were 10 successful collisions. Okay? So after another minute, there were only 8 successful collisions. And then there were only 6. So in total, yes, there has been 24. But for that minute, they are decreasing. So what do you notice about volume over time? The change in volume decreases every minute. How does that relate to collision theory? Well, as time goes by, there are less reactants and therefore less successful collisions. If you wanted to use your wording in terms of concentration, the concentration of the reactants decreased. Do you understand? Therefore, there are less successful collisions. Is that okay?
Yes.
Okay, it's not an easy question. It's a level 4 question, I think. Calculate the volume of hydrogen peroxide solution used in the experiment. Assume that 1 mole of oxygen occupies a volume of 24 cubic decimeters at 24. So if they ask you to calculate volume or grams, know that you are actually going to do your calculation in moles. So that's where we do calculation. We use moles for our calculations. But to get to moles, we need to use what they gave us and get into moles. Then, since they want to know how much volume, we need to convert our volume, our moles back into volume. So notice what they tell us, that they're asking how much hydrogen peroxide was used. What is calculate the volume of hydrogen peroxide used? Okay, so what we need to do is, all we know about the end result is what volume of oxygen was produced. Is it? Can you see what volume of oxygen was produced in the end?
In the end.
Yeah.
36.
Sorry? 36. So in other words, what we know in our reaction, what we know is that in the end, we had 36 cubic centimeters of oxygen. Okay. So we want to know how much mole is that. We want to convert so that we can do calculations. We need to, whatever we know in the end, we need to convert into moles. So now let's look at what they told us in the question. We can assume that 1 mole of oxygen occupies 24 cubic decimeters at 20 degrees Celsius. Okay, so 1 mole per cubic decimeter is equal to 24 volume. No, I lied. Sorry. One mole is equal to 24 cubic decimeters. Like that. That's what they give us. Is that okay? You don't like where this question is going. Okay, so we first see we need to convert. How do we go from cubic centimeters to cubic decimeters? No. Divide with 1,000. Okay, very important. 0,036 cubic decimeters. And so I want to know, and it's just the ratio. So I want to know 0, if I divide this side, I would say that 1 mole divided by 24 cubic decimeters must equal how many moles divided by 0,036 cubic decimeters. So I want to know how many moles do I have. So I'll take the ratio that was given. For every 1 mole I've got 24 cubic. So that ratio must equal the ratio of moles that I actually have. So I don't know how many moles I have. So I divide by the volume. In other words, this concentration must equal that concentration. That's basically, and concentration is mole over volume. Okay. So now all I do is I multiply both sides with the 0,036, and I get that the number of moles that I have of oxygen in the end is 0.036 divided by 24, 0,0015. Please don't round off until you get to your final answer. Okay, this is how much moles were produced. Now the question was, and now comes the calculations. When we do calculations, we use our equation. Okay, so we saw our equation was 2H2O2 decomposes into 2H2s plus O2. No, 2H2O plus O2. That was the original reaction. Okay, now we know that this was the amount of moles, and I like to use ratios. I don't like those ICE tables things. They don't communicate sense to me. But if you prefer those, that's fine. Okay, I'd rather say that the mole, if I take the mole of oxygen divided by the mole, and now I'm using the value that they're actually asking me, but divided by the mole of hydrogen peroxide, I must get, for every one of these, there must be one of those. So now I see, okay, I know how many moles of oxygen I had, 0,0015. I want to know how many moles of hydrogen peroxide was used, but I know that when I divide them with each other, I should get a half. And now I just solved this equation. It's probably better to actually swap them around, to have actually rather have started with the one you're looking for. I want to know how many moles of hydrogen peroxide. I know they're asking what's the volume, but you can't calculate volume. You have to calculate moles, and then you convert that into volume. So if they ask you for a certain gram or a certain volume or a certain anything other than mole, you know I'm going to calculate mole and convert it into that. Okay. So let's start by the mole I'm actually trying to look for, divided by the mole of oxygen that was used. I'll rather do this way. You'll just see it, and then I must just keep then in mind that now I must use the coefficients in the opposite direction. So in other words, the coefficient of this one is 2. 2 of these for every one of that. And then you see now when I substitute, it's much simpler to solve, because here in the bottom 0,0015 is equal to 2 on this side. I just multiply once. 0,015 times 0,0015. And then I find that the mole of hydrogen peroxide is 0,003. Okay. Now, I don't even do this calculation, because I can already see that for every 1 mole of this, I must have 2 mole of that. So for myself, I would have immediately seen I use double. Whatever mole I get for the one, I must use double to produce that. Okay, but that's okay if you use that. Don't feel intimidated by that. Okay, now that I know that this much H2O2 is 0,003, now I need to know what was the volume of this. And you'll notice that when they talked about the solution, they said that this much gram of manganese dioxide was added to and they gave me the concentration of the solution. So they told me that there were 2 moles per cubic decimeter in my solution, which again says that I have 2 mole is equal to 1 decimeter. Okay, or I can just look at it like this: 2 mole divided by 1 decimeter. Okay, this is what was given. What I want to calculate is I know that my moles is then, so I keep this ratio on this side, I have 0,003 moles, and I want to know what was my volume. Okay, or if you want and you insist on using the formula is just concentration is mole over volume. You have the concentration is 0,2, you have the mole is 0,003, you want the volume. Okay, you can't just use the formula, but I just want to show you don't need the formula. So volume, when you solve it, is 0,003 divided by 2. It was, yeah. So the volume is 0,0015 cubic decimeter.
What's the difference if you put a negative 3 and if it's just a normal 3?
Why would you want to put a negative 3?
What's the difference between the 2?
Well, you're working with moles. Is how can you have negative moles? Do you understand? There's no meaning in negative. Reaction rate, yes, can be negative because you're talking about moles per second. So if you are saying negative 3, then you means every second I'm losing 3. But when we just have pure moles, how many moles we're working on? No negative. But where did you see the negative?
No, sometimes like during equations or like when I check answers,
Okay.
solutions, they put like a negative.
Is it?
Yeah.
Yeah, I can only imagine that is if it was reaction rate, then yes, there can be a negative because that means I'm looking at the reaction rate for my products. No, sorry, reactants, because my reactants are decreasing. I'm losing moles every second. Okay. So here we go. We calculated the volume of hydrogen peroxide solution used. Okay. What mass of manganese dioxide would remain at the end of the catalyzed reaction? We started with 0,1 gram. How much will be left in the end? Sorry?
It will all be used up.
Is it confused?
Good. Correct him, please. What did we say? The catalyst. is a reactant and a product.
Yes.
Which, in other words, if I started with 1 gram, I must finish with 1 gram. Yes, it takes part in these intermediate reactants, but it always produces itself back again. Okay? So a catalyst must always be, all of the catalyst must always remain. It doesn't matter how much of the reaction took place. All of the catalyst. And that was really a complex question, I thought. Overall, that was a complex question, but when I actually, that's when I read it. I'm like, oh no, I don't know how to do this. But then when I attempted it just now for the first time, it wasn't that bad. Okay. Let's look at this one. Again, I haven't looked at these questions. So let's if we can do it. Define the term reaction rate in words. Whenever you see rate, you'll see there's 2 marks. Whenever you see rate, you can always use per second or per time unit. Whether it's per second or just be safe and use per time unit. So in physics, for example, we have that the net force is equal to the rate of change in momentum. The net force is equal to the rate of change in momentum, which means that as momentum change per unit of time, that gives me the net force acting on the object. So change in momentum over change in time. So reaction rate, at least something in your explanation must refer to per unit of time. Okay, that's good. The change in moles per unit of time. That's good. Good definition. Okay, you could say it's related to the number of successful collisions per unit of time, or in a reaction. So that could also be, but yours is 100% accurate. Learners use the reaction between impure powdered calcium carbonate and an excess of hydrochloric acid to investigate reaction rate. So there's a powdered being added to, or probably the other way around, to investigate the reaction rate. The balanced equation for the reaction is, that was kind of them, to give you the balance. There's calcium carbonate plus 2 hydrochloric acids produce calcium chloride, water, and CO2 gas. They perform 4 experiments under different conditions of concentration, mass, and temperature, as shown in the table below. So you'll notice remember when we looked at, if they say different conditions, they look at concentration. What concentration was changed? Which one's concentration? If they say different conditions, which means they changed things over time, what did they change? If they changed concentration. There? Which one uses volume? See, they can't affect, if they change conditions, they can't change the reactant's condition. The product's condition. They can only change the reactants. So again, guys, go back to what we said before. There are 3 things you can do to increase reaction rate. 1 is you can add a catalyst. 2, you can increase temperature, which means you increase kinetic energy. 3 is you decrease the chance of unsuccessful collisions. Now, it depends on what am I using. If I'm using a gas, I would decrease the volume, in other words, increase pressure. If I work with an aqueous solution, I would increase concentration. If I work with a solid, I would grind it into a powder or make it increase the surface area. So if they said different conditions, if they could change concentration, what did they change? Whose concentration did they change? Yes, the AQ one. Okay, so hydrochloric acid, they changed mass and temperature. Okay, what do they mean by they changed mass?
Isn't that like the amount of the certain substance?
Yeah. Now, would you increase the reaction rate if you increase the amount, the mass?
I guess if there's more reactants human for more products, but I don't think that would affect the reaction.
No, it wouldn't. It wouldn't affect the reaction. It shouldn't. Okay, because if I have one container here, just by doubling this container with reactants, I've increased the mass. Doesn't necessarily. But if I add another scoop of powder without necessarily increasing then I'm allowing for more of the reactant to have surface area. So it depends now on how they're going to change it. I don't know. Just in general, mass, just increasing the mass doesn't change your reaction rate. Depends on how you increased it. They use identical apparatuses in the 4 experiments and measure the volume of the gas released in each experiment. So very similar to the previous one. What are they measuring in the end? So they're going to do a very similar experiment. They have a tube connected to a syringe and they measure the amount. But what would be in that syringe?
Gas.
What gas? Carbon dioxide. That's what they're releasing, okay? The results of experiment 1 and 3. So here's the 3 experiments. They don't say, so under each experiment it seems like there were different conditions. Okay, they talk about the concentration, the mass of impure calcium carbonate. Okay, so there's only in one experiment where they actually change it, and then the initial temperature. In other words, the temperature at which they took it. Write down the results of experiment 1 and 3 are compared in the investigation. Write down the independent variable. Now, the independent variable is a variable that you can change. The dependent variable is the observation that changed because of the change that you made. In other words, it's a change that happens that depends on something that you, while conducting the experiment, actually changed. So the independent variable, if we look at experiment 1 and 3, what do we find? What did we change in that experiment?
Concentration. So,
Experiment 1 and 3. What changed?
initial temperature. So,
The initial temperature. Is that something that changed because of something else? Or is it something that I changed? That the experiment has changed? Yeah, it's something that we changed. And that caused what? What are they investigating? They're investigating reaction rate. So what is going to influence what? Is reaction rate influencing temperature, or is temperature influencing reaction rate? So what is independent? Which one is depending on the other one, and which one is independent of the other one?
Isn't temperature independent?
Temperature is independent. So again, temperature is the thing that I would change, because I changed as the experimenter the independent variable. The dependent variable is the variable that changes because of a change that I've made. And so your independent variable is temperature, dependent variable is reaction rate. Okay. Or if you did say volume, that would also be fine. I think that's probably more correct, because that's what they're observing, is the volume of gas. But they are using that to investigate reaction rate, so I don't think it would be wrong if you say reaction rate. Use collision theory to explain why the reaction rate in experiment 4 will be higher than in experiment 3. What is the difference between 3 and 4?
Mass and temperature.
The mass. Now, again, mass does not necessarily mean that there's a difference in reaction rate. If they do say that there is a difference, why is there a difference? So forget about what the reason is. Why would one reaction rate be higher than another reaction rate? The general answer.
Because you have to confuse
No.
that.
The general answer. Why is one reaction rate quicker, more than another reaction rate?
Catalyst.
No, I'm not asking for a reason. I'm asking, what is the difference? Like, what does it mean if I'm saying my reaction rate is more? Not what causes it. What does it mean if my reaction rate? In collision theory, we're talking about collision theory. That's it. So there's 1 mark already. There's 3 marks. 1 mark is going for you mentioning that there are more successful collisions. Okay. Now, why is the collision successful?
Because there's enough kinetic energy.
Okay, there's enough kinetic energy, but for these two, is kinetic energy the difference between these two things? No, that would have been the difference when the temperature was different. So they've got the same kinetic energy. So we need to now explain, why are there more successful collisions? So it's not kinetic energy. Is it a catalyst? Does the one have more catalyst than the other one? No. They both, I don't even know if there was a catalyst in here. Okay, but it's definitely not the catalyst. So it wasn't that the activation energy of the one is less. Okay, so what's the only other explanation? So far we say there's more successful collisions. Now we need to say, why was there more successful collision? They ask us to explain. So again, there's those 3 things. We've already eliminated temperature and catalyst. So there's only one reason why there can be more successful collisions.
Pressure.
No, the third thing is broken up into 3 parts, depending on what my reactant is. But what is the third thing? The first one was an increase in kinetic energy. The second one was a decrease in activation energy. The third one was a decrease in the probability of non-collisions. Now it depends on what my reactant is. So I must go and look, what is the difference? We have a difference in the mass of calcium carbonate. What is calcium carbonate? It's a solid. When does a solid have a higher probability of successful collisions? That's not the answer.
Could it be got a larger surface area?
Yes. That can be the only answer. If the difference between 2 experiments is that the one has more solid than the other one has a solid, the only reason is because there is more surface area. Now, if you think of how this experiment might be done, is we have hydrochloric acid in a container. Now we're adding a little bit of powder, okay? And every little grain of powder has area that's connected to hydrochloric acid. Is there hydrochloric acid so hydrochloric acid is an aqueous solution, which means it's a liquid. It's in liquid form. Are there parts of the hydrochloric acid that can still touch other surfaces? What I mean, and it's now difficult for me to explain. Maybe I must draw it here. So here is a liquid. There is my powder at the bottom. The only part of the hydrochloric acid that's reacting is the hydrochloric acid that's touching this powder. So there's much more hydrochloric acid available. So the moment I add more powder, I am increasing the surface area of the reactants. Does that make it? But it's not necessarily the case, because if I had one powder and I added to that powder another powder, okay, notice it's not like with liquid where I have extra powder at the top. Okay, so in a liquid, yes, then there's more probability of that. Okay, so but anyway, you didn't even have to understand that. All you need to know is if one thing has a different reaction rate than another thing, it's because of one of three reasons. Either there's a catalyst difference, there's a increase in temperature difference, or there's less unsuccessful collisions. Now, if it's that one, I just need to go and determine what is that. Is it volume in the case of gas, concentration in the case of aqueous solution, or surface area in the case of solid? And now, since this is talking about a solid, it can only be that. And it does make sense if I increase mass that in this case I'm increasing the surface area in contact with the hydrochloric acid. Okay. The learners obtain graphs A, B, C, and D below from their results. Which one of the graphs A, B, C, or D represents experiment 1? Okay. Fully explain your answer by comparing experiment 1 with experiments 2, 3, and 4. Let me reduce it a little bit so you can see both at the same time. What do you think? It might even be best to just compare. Well, let's first look at A, B, C, and D. Which one has the highest reaction rate? Why?
It's got a steeper gradient.
It's the steepest gradient. If I had to climb any one of those, I want to climb D. Okay. Because A is way too steep. Which means A has the most favorable conditions, isn't it? Which means if there was a catalyst, there's not. Okay, he would have had the catalyst. Would he have the highest or the lowest temperatures? The highest temperatures. He's got the highest reaction rate. Does he have the highest or lowest concentration? Because here, our reactants are both solids and aqueous solutions. So here I could do both. I can increase the concentration and I can increase surface area. Okay? And you'll notice for A, he probably has increased temperature, increased concentration, increased surface area. Which one would that be? Which one has overall the most favorable conditions of 4? 4 has doesn't have the lowest concentration. He's got the highest mass, and he has, of the temperature, the highest temperature. So that's definitely him. Which one of those experiments do you think, or first, which line represents the lowest reaction rate? D, because it's on. Which one of those represents the lowest, least favorable? Would you agree to? Okay. Again, compared to these three, at least he's got the same amount of gram, but he's got the lowest concentration and the lowest temperature. Of the two temperatures, it's the lower temperature, so that would be D. Okay, so we've already assigned A and D. Now it's between B and C. Which one will go to 1? So we're left with experiment 1 and 3. Between experiment 1 and 3, which experiment will have the highest reaction rate? Now I'm asking between 1 and 3, which one will they have the highest reaction rate? 3, because of temperature. So in other words, between B and C, B will be 3. So we said this one is 4, 3, 2, 1. Okay, and so here they ask us which one of the graphs A, B, or C represents experiment 1. And we saw that that would be D. And now everything that we talked about now, you will have to explain. And that for 6 marks isn't that bad. Okay, just give your reason for why A is the highest, why D is the lowest, and why B is higher than C. Or in this case, why 1 represents the lowest reaction rate for the highest, and why 3 would have a higher reaction rate. And then obviously you have to talk about gradient, because the reaction rate is represented by the gradient. So you have to mention that. Okay, when the reaction in experiment 4 reaches completion, the volume of gas that is formed is 4,5 cubic decimeters. Assume that the molar gas volume means how many moles per gas volume, is at 40 degrees is equal to 25 cubic decimeters. So 1 mole would be 25,7 cubic decimeters. Okay, it's the same question that we just answered. They asked, calculate the mass of impurities present in the calcium carbonate. Okay, I also have to think before I answer these things. At least one thing that I want to know is calcium carbonate Oh yeah, okay. So in this reaction, they should tell us the mass used. Maybe not. Okay, I can go. It's easy to calculate. Well, it's not easy. It's a process to calculate the calcium carbonate, and that will roughly give you 3 to 4 marks at least. Okay, which would be the same thing. We have volume, but we can't do calculations on volume. So I'll use my volume to go calculate how many moles. They give me the volume of carbon dioxide produced. So I can go and work out the moles of calcium carbonate produced, not calcium carbonate, carbon dioxide. Then I can use that together with the ratios here to find out what was the ratio of calcium carbonate that was used. Okay, because for every 1 mole of carbon dioxide, I will use 1 mole of calcium carbonate. Okay. When the reaction in the experiment, oh, okay, good. They give us that we're working with experiment 4. So in experiment 4, we know that we have 25 grams of calcium carbonate. So, and this is impure calcium carbonate, which means there's other things other than calcium carbonate, but 25 grams is this, all of this. So I'm going to now use my experiment. So I tell my experiment 4, I'm going to use to calculate the number of moles in the end that was used, and then I'm going to work out, well, how many grams was used. Okay. Whatever was not used was impurity. It couldn't react because it was impure. Which means whatever's left, so 25 is what I had. Let's say I use about 23 grams, then there were 2 grams impurity. I'll do the calculation now so you can see. I'm just trying to show you, when I look at this, I have to reason it out as well. So I know how to get calcium carbonate that was used. But they want to know the impurities, which means how much was not used. And so I cannot know how much was not used if I don't know. So I know how much reacted, but how much did I add to begin with? Okay, so let's quickly do that. It shouldn't take long. So once again, I'm going to follow my system of using ratios. So it says that that this is the amount of volume. So let's do it now a little bit more systematic. I want to go and work out the number of moles for carbon dioxide, because that's what they gave me. That's what I know. I know in carbon dioxide that the volume of carbon dioxide that I have is, so let me write it like this, the moles of carbon dioxide divided by the volume of carbon dioxide. According to them, it says that for every the molar gas volume, which means 1 mole of gas, takes a volume of 25,7. So this must equal, for 1 mole must be 25,7 cubic decimeters. And now I just replace what I do have. I don't know the moles, but I do know the volume that was produced, 4,5 cubic decimeters. So 4,5 cubic decimeters. And this must give me 1 over 25,7. And so when I just multiply both with that 4.5, then the moles of calcium carbon dioxide, what the heck, 4.5, 25,7, 4.5. So I'm going to roughly here say that's roughly 0,1751, 0,1751, but I'm in my calculation going to use that answer on my calculator. Okay, then I know, okay, now according to now I can do my calculation of that conversion. I'm given the information about carbon dioxide, but I want to know about calcium carbonate, which means where is the relationship? The relationship exists in the formula. And this is now where I need to go use moles. Now I use my moles and my formula and the ratio given in the formula. So in the formula, what is the one I want? I want the moles of calcium carbonate. The moles of calcium carbonate. And I know if I divide the moles of calcium carbonate with the moles of calcium of carbon dioxide, it must be the coefficients of the two. So this is 1 divided by 1, which is just 1. Now again, that just means that they're going to have the same. So you could just immediately say, oh, well, that means that the mole of calcium carbonate is also equal to 0.1751, roughly. Or you could go and substitute it in there, multiply both sides, and get the exact same answer. Okay? Then, now that we know how many moles of calcium carbonate, we want to know what mass does this represent. Okay, and we know the mass, hopefully you know the mass formula is mass is equal to moles times molar mass. Okay, that's that. It's on your formula sheet, but N is equal to M over capital M. So I just want M, so it's actually this triangle. N is M over capital M. So if I want mass, I take moles times molar mass. Okay, and for calcium carbonate, that is the moles is this 0.1751 times, and now the mass of this is, I'm going to have to look here, calcium is 40, yeah, 40, 40, 12 and 16, so it's 40 plus 12 plus 16 times 3. 16 times 3 is 48, so it's 82, so it's 100. 100. So roughly the mass is 17,51 grams, or this answer just times 100. 6 times 3 is 48 plus that is 88 plus 12, yeah, 17,51 gram. You with me? This is how much mass of calcium carbonate was used up, but we had 25 grams. So if we answer the question, calculate the mass of the impurities. What is the mass of the impurities? Yes, you have the right idea. How would you work it out? 25. That's how much we used, minus 17,51 is actually 7,49 grams. Okay. Get that? Yeah, not that difficult. Okay, but it is level 3 type question, so yeah, it seems like a standard way of asking these questions.